In the last video, we started talking about rationalization of surds, and then we saw why exactly it is necessary to rationalize surds, and we saw that it is good for simplifying algebraic expressions. We saw that it is actually good for mathematical notations because it is prettier to divide by rational numbers as compared to irrational numbers that we have for surds. And then finally, there's a historical context where rationalization is actually pretty, though it's not mathematically required. So in this video, we're looking at rationalizing a single surd in the denominator. We've done it a couple of times, but we just want to look at it more intently. So rationalizing a single surd in the denominator. So the learning objectives, by the end of this lesson, you should be able to understand what a surd is. I mean, you already do that. But if this is your maybe this is the first video of mine you're coming across, maybe you have not been following the whole series on surds. But and if you want to see all the playlists I have on my channel, just click on playlist. So you see all the playlists because I take the videos from the very basic concept to very advanced levels, right? So I have some videos coming already on such. So I've explained all that, but I mean, I also always take the opportunity to explain it again in case this is one of video you're seeing. So rationalizing a single cell in the denominator, you want to understand what a surd is, explain what rationalizing the denominator means, and use the method of multiplying by root b over root b, because it is a single surd in the denominator we are considering here. Then simplify expressions step by step and rationalize fractions containing a single surd in the denominator. Okay, so again, to refresh our memories, or if this is your first time of coming across the idea of surds, it's clear, it should be known that a surd is a root that cannot be simplified into a rational number. Examples of surds include root 2, root 3, root 5. So if try hard as you may, you cannot actually get these numbers to become rational ratios of rational numbers. You cannot get them to become rational numbers. A rational number is a ratio of two integers, so you can't express any of this as all that. So these numbers are irrational because their decimal expansions never terminate and never repeat. So examples that are not surds, root 4 is not a surd because root 4 is 2, and 2 is a rational number because you can say 2 over 1, and 2 is an integer, 1 is an integer. So you can express, so in essence, we can express root 4 as the ratio of two integers. Same for root 9. So root 4 and root 9 are not surds, but root 2, root 3, root 5 that cannot be expressed as rational numbers are actually surds. So this simplified to integers, so they are not considered. So that's for root 4 and root 9 now. Okay, so next we look at fractions containing surds. So sometimes surds appear in the denominator of a fraction. An example is 3 over root 5. So mathematicians prefer expressions where the denominator is rational, that is, contains no roots. We don't want that radical of square roots. So to achieve this, we use a process called rationalizing the denominator, which is a pretty simple process. And this is you'll see the idea very soon. So rationalizing the denominator means rewriting a fraction so that the denominator does not contain a surd. So that is what it means to rationalize the denominator. So you have 3 over root 5. So we transform it into an equivalent fraction where the denominator becomes a normal number. So instead of having root 5 here, we want to have another number here that is not irrational. Okay. So the key idea is that if the denominator contains root b, we multiply the fraction by root b over b. You know, root b over b is 1. This works because root b over b is 1. And when you multiply anything by 1, it doesn't change. So the expression remains the same, though its form has been transformed. It has been changed because it's quantitatively exactly the same thing, but you have just made it prettier by rationalizing. So multiplying by 1 does not change the value of the expression, right? However, it changes the form of the fraction so that the denominator becomes rational, which is our goal ultimately when that's why we talk about rationalization. So you're making an irrational denominator into a rational one. So important property of square roots. So a key rule used when rationalizing is that the square root of a multiplied by the square root of a gives a. Example, square root of 5 multiplied by 5 is 5. This removes the square root from the denominator. So if you multiply a surd by itself, it removes the radical. That's the essence of doing that. So the general formula is then that if we have a divided by root b, you multiply by root b over b because b is down there, all right? And then you have square root of b all over square root of b, which is 1. So you then have a divided by square root of b multiplied by root b divided by root b. So it's more or less like you're multiplying by 1. If you multiply this out, you have a root b all a root b. That's a times root b. That's a root b. Root b times root b. That's root b squared, which is b. So now this a root b over b is prettier than a over root b. Mathematically and conventionally. So this removes the surd from the denominator. Now I know you can have a confusion, right? What if the expression you actually have is root a over root b? So can you be tempted to say this is root a over root b multiplied by root a over root a? This won't work because our focus is on making sure that the denominator is one is not does not contain this radical square root. So what you do is root b. So if you have roots up and down, don't make the mistake of multiplying by root a over root a, multiply by root b over root b, which is the denominator. So you have root b over root b like that, and then that means you have if you multiply this out, you have square root of ab all over square root of b, square root of b times square root of b, that's square root of b squared. So that'll be root ab all over b like this. So that's like having 1 over b roots ab if you like. And that's that. So if you have roots up and down, don't forget the rationalization is based on the roots down at the denominator. So this because you want to remove the surd from the denominator, that is what rationalization means. So step-by-step method then means that to rationalize a denominator containing a single surd, identify the surd in the denominator, not in the numerator. Then multiply the fraction by root b over b, multiply the numerators, multiply the denominators, and simplify the result, like we just did up there. And then we'll see plenty of examples to practice with. So imagine this one now. You have 1 over root 2. So we don't have a problem having it this way because these days you can punch your calculator and get your result. But multiplying, but to rationalize, you now multiply root 2 by root 2 over root 2 because we have root 2 down here. So 1 over root 2 times root 2 over root 2. Then multiply the numerator. So you have 1 times root 2, that's 2 root 2. Root 2 times root 2, that is 2. So the whole expression is now root 2 over 2. And so that you can understand that 1 over root 2 and 2 root 2 over 2 are not different. So you want to check 1 divided by square root of 2. That's 0.7071. And then the new thing we have is square root of 2 divided by 2. Exactly the same expression. So but rationality just makes it prettier. Example 2, you have 4 root 7. So you have 4, you want to rationalize 4 over root 7. So step 1, multiply by root 7 over root 7. So you have 4 over root 7 times root 7 over root 7. So expand, you have 4 root 7 divided by root 7 times root 7, that's 7. So that's 4 root 7 over 7. So to be sure, you have the same thing. So you have 4 over root 7. So you want to check if it's the same as 4 root 7 over 7. So you have, okay, let me just use this. I have 4 over root 7. And then after rationalizing, we have 4 root 7 all over 7 now. So exactly the same, 1.51, blah, blah, blah. So that tells us that we are good. So we have just made this prettier. So in example 3, you have okay. Now, for example, 3 things I beat not so straightforward. You have to simplify first. So you have 6 over root 2. So for 6 over root 2 now, um, well, you could rationalize with root 8, but it's better you simplify first to the basic form before you continue. So root 8, is root 4 times 2, which is root 4 is 2 and root 2 remains. So that means you have 6 over 2 root 2. And if 2 can even divide 6, so 2 here is 1, 2 here is 3. So you have 3 over root 2. Now you can rationalize that now. So you have 3 over root 2, where you multiply by root 2 over root 2. That's 3 root 2 all over 3 root 2 all over 2, right? For the numerator. So 3 root 2 for the numerator, for the denominator, root 2 times root 2, that's 2. So the final answer is 3 root 2 over 2. Again, that's what we are looking. We started with 6 over root 8 and we ended with 3 root 2 over 2. So let's do 6 over root 8 first. So this is 6 up here divided by square root of 8 down there. That's 2.121 and all that. And then the final result we got is 3 root 2 over 2. 3 root 2 over 2. So we have 3 root 2 all over 2. 3 root 2 over 2. And that's what we have. Oh, okay, no, 3 root 2 over 2. So we have 2 points, exactly the same result. So 6 over root 8 is basically the same thing as 3 root 2 over 2. So rationalizing just makes things prettier, basically, it doesn't change anything because in the process, you technically just multiplied by 1 cleverly, right? So you want to rationalize 7 over 2 root 5, so root 5 is the radical term here. So you multiply by root 5 over root 5, which is like multiplying by 1. So you have 7 over 2 root 5 times root 5 over root 5. So you have 7 times root 5, 7 root 5, 2 root 5 times root 5. That's 2 root 5 times root 5, which is 2 times 5, 10. So at the end of the day, you have 7 root 5 all over 10 as the final result. So again, you want to check that 7 over 2 root 5. So over you have 7 over 2 root 5. The answer is 1.5652, blah, blah, blah. And then the final result, 7 root 5 over 10. 7 root 5 7 root 5 divided by 10. So you see exactly the same thing. So rationalizing just makes things pretty and it doesn't change it in essence. So some common mistakes you should be wary of. First of all, mistake one, multiplying only the denominator. So it is incorrect to just say 3 over root 5 times root 5. Root 5 will cancel out and you get 3. That's totally wrong. They won't give you the same result. So you must multiply both numerator and denominator. So it should be 3 over root 5 times root 5 over root 5, because by doing this now you are not maintaining the expression because you have not multiplied by 1. So this is a mistake you should avoid. Number two, forgetting the square root rule. So you remember that square root of a times square root of a is a. So that's why by the time you say you have 3 over root 5 times root 5 over root 5, so you have 3 root 5 up there all over root 5 times root 5 should give you 5. Then the third mistake you can make is not simplifying first. So if you have 5 over root 12, so it is better. Of course, it's not like if you don't simplify first, you won't get your result. But you can make your life unnecessarily difficult, right? You get your result, but it's easier to multiply to simplify first. So you have 5 over 2 root 2. It's better to work with this than to just say 5 over root 12 times root 12 over root 12. You get your answer, but it's better to simplify first. So that's a mistake, but maybe not such a grave mistake, like in multiplying only the denominator. But I mean, it makes things easier. So that we are here with the practice problems now. As usual, I'll take one and then move on to others. Yeah, let me take this question 8, which is 8 over root 15, because okay, even there's no simplification, and I'm looking at the possibility of needing to simplify. Mm, yeah, oh, no big deal. So I think. Let me just take number 10. 10 over root 7. We want to rationalize that. 10 over root 7. 10 over root 7. Is it 7 or 17? I think it's 17. 10 over root 17. 10 over root 17. Yeah, that's 10 over root 17. So that's the same thing as, okay, 10 over root 17. So that's 10 over root 17 multiplied by 1, technically. And that's the same thing as 10 over root 17. If you multiply by 1, nothing has changed, right? And 1 in this form, because we have root 17 as the denominator, we multiply by root 17 over root 17, which is still 1. So if you multiply all the numerator, that's 10 root 17 all over 17. Because root 17 times root 17 is root 17 squared, which is simply 17. So you can check to be sure 10 over root 17 is the same thing as 10 root 17 over 17. Okay, so you have 10 over root 17 all over. So you get that the result there. And that's now we say that is 10 root 17 all over 17. So you see, they're exactly the same thing. So that's question 10 there. So I go on to question 20. Yeah, I think I want to take 20. So we have 12 over root 27. 12 over root 27. So we have 12 all over root 27. So you want to simplify first. This is 12 all over root, so the biggest square root there is 9. So you have the biggest square rather is 9. So 9 times 3. So you have 12 over square root of 9 is 3. So you have 3 root 3. So after this now, you can then say this is 12 over 3 root 3 multiplied by 1. Nothing changes. And in this case, you have 12 over 3 root 3. So 1 can, in this case, can now be root 3 over root 3. That's the radical part. So you just focus on that. Then you can multiply. You have 12 times root 3. That's 12 root 3 all over 3 root 3 times root 3. That is 3 times 3. All right, because root 3 times root 3 is root 9, and square root of 9 is 3. Okay, maybe I should take it step by step. Not necessary, but it's okay. Root 3 times root 3 is root 9. So you have 12 root 3 all over 3 times 3. So that is 12 root 3 all over 3 times 3 is 9. So 3 here is 4, 3 here is 3. So we have that to be 4 root 3 all over 3. And that is the result. 4 root 3 over 3 is the same thing as 12 over root 27. You want to check that using your calculator. 12 over root 27. So 12 over root 27. That's what we have there. Then the final result is 4 root 3 over 3. 4 root 3 over 3. So this is 4 root 3 divided by 3. So exactly the same expression right there. Okay. So with this, we come to the end of this interesting video about rationalizing, uh, rationalizing a single surd in the denominator. So you just multiply by something like root b over b, where root b is the denominator of the surd you're trying to rationalize. So don't forget to try your hands on the practice questions so you can actually get used to the idea. And then, of course, let me know how helpful this is for you. And if there's something else you like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, question is, why have you not? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can as well become a member of this channel by clicking on join. You have 3 levels of membership with 3 different levels of special benefits. All right, you want to avail yourself of all of that so that you can, get more value from this channel. So part of the benefits you get is maybe get to see some videos first, and sometimes some videos that totally made for you as a member, and others who are non-members don't have access to such videos. Then apart from that, you can also request for PDF copies of my notes. We can hang out together to discuss whatever you interest you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.